Basic transformation, translation, rotation, scaling. Basic transformations comprising translation, rotation, and scaling are foundational concepts in computer graphics and geometric modeling. These transformations enable the manipulation and positioning of objects within a coordinate system, facilitating the creation of complex scenes and animations. Translation. Translation involves shifting an object from one location to another within the coordinate space. In 2D graphics, translation moves objects along the x-axis and y-axis, while in 3D graphics, it includes movement along the z-axis. By altering the object's position, translation allows for the creation of motion and spatial arrangements. Rotation. Rotation entails the transformation of an object by rotating it about a specified point or axis. In 2D graphics, rotation occurs around a point, typically the origin, by a defined angle. In 3D graphics, rotation can be performed around various axes, x, y, and z, altering the orientation of objects within the scene. Rotation is essential for creating dynamic and visually engaging animations. Scaling. Scaling involves the resizing of an object either uniformly or non-uniformly along different axes. Uniform scaling preserves the object's of proportions, whereas non-uniform scaling allows for independent resizing along each axis. Scaling is crucial for adjusting the size of objects relative to one another and for creating depth and perspective within a scene. These fundamental transformations serve as building blocks for more complex operations in computer graphics, such as deformation, morphing, and skeletal animation. By combining translation, rotation, and scaling, artists and developers can achieve a wide range of visual effects and manipulate objects with precision and creativity. Transformations for complex movements. Transformations for complex movements in computer graphics often involve combining multiple basic transformations, translation, rotation, scaling, in sequence of currently. Here are some techniques used for achieving complex movements. Keyframe animation. This technique involves specifying key poses or frames at certain points in time and interpolating between them to create smooth motion. Each keyframe typically contains transformation parameters such as position, rotation, and scale, and the other computer interpolates the transformation between keyframes to generate the animation. Hierarchical transformations. Objects in a scene can be organized hierarchically with parent-child relationships. Applying transformation to parent objects affect other child objects as well, enabling complex movements like character animations. For example, rotating a character's torso will also rotate its limbs if they are attached as child objects. Path animation. Objects can be made to follow predefined paths or curves in the scene by interpolating along the paths and adjusting orientation and scale as necessary. Complex movements such as object following curved trajectories or camera movements along specific paths can be achieved. Blend shapes, morph targets. In character animation, blend shapes allows for the interpolation between different mesh shapes. By blending between various facial expressions or body poses, complex movement like facial animations or character deformation can be realized. Physics-based animation. Simulating physical properties like gravity, friction, and collision detection can lead to complex and realistic movements. Objects respond dynamically to external forces, allowing for natural-looking animations such as cloth simulation, rigid body dynamics, and fluid simulation. Inverse kinematics. Inverse kinematics enables the manipulation of articulated objects like character limbs or robotics arms, by specifying the desired position or orientation of an end effector, example, hand or gripper. The system then calculates the necessary points angles to achieve the desired end position, facilitating complex movement like reaching, grabbing, and walking. Procedural animation. This approach involves generating animations algorithmically rather than specifying them explicitly. Techniques such as procedural noise, procedural modeling, and procedural motion can create complex and dynamic movements that respond to various parameters or inputs. By combining these techniques and leveraging the capabilities of modern graphics, hardware, and software, developers and animators can create highly realistic and captivating animations with complex movements. Advanced Transformations Perspective. Advanced transformations in computer graphics often include perspective transformations, which play a crucial role in creating realistic three-dimensional scenes. Unlike basic transformations like translation, rotation, and scaling, perspective transformations simulate how objects appear smaller as they move farther away from the viewer, creating depth and realism in the scene. Here's an introduction to perspective transformations. Perspective projection. Perspective projection is a transformation that maps 3D points in the scene to 2D points on the screen, taking into account the viewer's perspective. This transformation simulates how objects appear smaller as they move away from the viewer, creating the illusion of depth in the rendered image. Vanishing points. In perspective projection, parallel lines in the 3D scene converge to vanishing points on the projection plane. This phenomenon mimics how parallel lines in the real world appear to converge at a point in the distance when viewed from a specific vantage point. Depth cueing. Perspective transformations often include depth cueing techniques to enhance the perception of depth in the scene. Depth cueing involves adjusting the color, brightness, or blur of objects based on their distance from the viewer, making objects far away appear fainter or less distinct than closer objects. Field of view. Perspective transformations can also incorporate a field of view parameter, which determines the extent of the scene visible to the viewer. A wider field of view results in a more expansive view of the scene, while a narrower field of view creates a more zoomed-in perspective. Camera parameters. Perspective transformations are influenced by camera parameters such as position, orientation, and focal length of the virtual camera. Adjusting these parameters can alter the perspective of the rendered scene, allowing for different viewpoints and compositions. Frustum clipping. Perspective projection often involves clipping objects that are outside the viewing frustum, which is the pyramid-shaped region of space visible to the virtual camera. This prevents objects from being rendered incorrectly and improves performance by reducing unnecessary computations. Projection matrices. Perspective transformations are typically represented using projection matrices, which map 3D coordinates to 2D screen coordinates. These matrices incorporate parameters such as the field of view, aspect ratio, and near and far clipping planes to accurately project the scene onto the screen. Overall, perspective transformations are essential for creating realistic and immersive three-dimensional graphics, allowing developers to simulate the effects of depth